Section: Introduction. In this section, we discuss the advancements in large language models, LLMs, and their extension into multimodal large language models, MLLMs, or vision language models, VLMs, like GPT-4 and Gemini. These models aim to understand and generate content across different types of data, such as text and images. Early methods combined language models with diffusion models to handle text and images separately. Later, autoregressive methods simplified this by using a single transformer model for both types of data. We also note that while recent work has focused on model architecture and pre-training strategies, there is a significant gap in exploring what happens after training, especially in non-autoregressive contexts. To fill this gap, we systematically explore the design of unified multimodal diffusion foundation models and introduce a new framework that enhances both architecture and training methods. Our contributions include: 1. Unified Diffusion Foundation Architecture. We present MMaDA, a type of diffusion model that transforms traditional generators into versatile task solvers through a shared probabilistic approach, removing the need for specific components for different modalities while still performing well across tasks. 2. Mixed long-COT post-training. We introduce a mixed long chain of thought fine-tuning method for cold start training. This method aligns reasoning processes across different modalities, promoting synergy and intermediate reasoning before generating final outputs. 3. Unified Reinforcement Learning, UNI-GRPO. We develop a reinforcement learning algorithm focused on diffusion, which enhances the model's reasoning capabilities and ensures factual consistency in its outputs. 4. State-of-the-art performance. MMaDA demonstrates superior performance in 3 key areas: textual reasoning, multimodal understanding, and text-to-image generation, outperforming both autoregressive and diffusion-based models in accuracy, efficiency, and adaptability. Next, we describe our data tokenization approach. We use a consistent tokenization strategy for both text and images, allowing the model to work under a single objective of predicting masked tokens. For text, we utilize the tokenizer from LLaDA, while for images, we use a pre-trained image quantizer from Show-O, which converts images into sequences of discrete tokens. For instance, an image is transformed into a sequence of tokens, enabling effective modeling for both understanding and generation tasks. Finally, we propose a unified probabilistic framework for pre-training that integrates various modeling objectives into a single architecture. This approach simplifies complexity and introduces a unified diffusion objective for both visual and textual data. By aligning the processes of noise corruption and semantic recovery, we facilitate better interactions between different data types during pre-training. Specifically, we train MMaDA to predict masked tokens for both images and text, using a unified loss function that focuses only on the masked tokens. Section Summary. In this section, we introduce MMaDA, a unified multimodal diffusion model that integrates text and image processing through a consistent tokenization strategy and a streamlined probabilistic framework. Our approach enhances cross-modal interactions and achieves state-of-the-art performance across various tasks by employing mixed long chain of thought post-training and a unified reinforcement learning algorithm. Section: Cold Start Long COT Data Curation. In this section, we explore how chain of thought (COT) mechanisms can improve post-training for our unified multimodal diffusion framework and enhance cross-modal interactions. To achieve this, we create a compact dataset of long COT trajectories focused on 3 main tasks: textual reasoning, multimodal reasoning, and text-to-image generation. This dataset supports stable post-training of our pre-trained MMaDA model based on several principles. First, we establish a unified COT format. A significant issue with vision language models is the variety of output formats for different tasks, such as text and image generation. We propose a task-agnostic COT format where the reasoning process is documented step by step before reaching the final output. This consistent structure helps connect different types of outputs and allows knowledge to flow between tasks. For example, Better textual reasoning can lead to more realistic images by aligning the logic of text with visual creation. Next, we focus on diversity, complexity, and accuracy. We utilize large open-source language and vision language models to generate a variety of reasoning trajectories across tasks. To ensure high quality, we use advanced models to filter out any inaccurate or superficial reasoning, selecting only the best long-form COT samples. Unlike previous models that aim for general understanding, our MMaDA is specifically designed for reasoning-heavy tasks, such as solving mathematical problems, and for generating images that require factual accuracy. We then introduce mixed long COT fine-tuning. Using our unified diffusion architecture, we create a mixed task long COT fine-tuning strategy to optimize the model across different tasks. This method not only improves task-specific skills but also sets a strong foundation for future reinforcement learning stages. The training process includes retaining the original prompt while masking certain tokens in the results. We then combine the input and compute the loss using our pre-trained mask predictor, allowing the model to fill in the masked areas based on context from both the prompt and the altered result. This approach ensures the model learns to recover masked tokens while staying aligned with the original prompt and reasoning logic. With our mixed long COT fine-tuning, MMaDA can generate coherent reasoning chains before producing final outputs. To further boost its performance on knowledge-intensive tasks and complex reasoning scenarios, we propose UniGRPO, a new reinforcement learning algorithm designed for diffusion models. This method creates a training framework that aligns task-specific goals across various modalities and reasoning styles. It consists of two main parts: a unified mathematical approach for reinforcement learning in diffusion and a diverse reward system to connect policy gradients with specific task rewards. We also address the challenges of adapting the original GRPO to diffusion models. The original GRPO calculates token-level probabilities and sequence-level likelihoods efficiently in autoregressive models. However, diffusion models present three main challenges: the dependency of token-level probabilities on masked regions, the need for a consistent mask ratio for approximating policy distribution, and the inability to directly accumulate sequence-level likelihoods from token probabilities. Previous methods have tackled these issues with less effective strategies. To address these challenges, we introduce UniGRPO, a more efficient approximation algorithm for diffusion models. In this approach, we fix each response during gradient updates to ensure stable policy evaluation. We implement a structured noising strategy where we uniformly sample a masking ratio and create a perturbed version of the response by replacing tokens with a mask. This method maintains randomness while exposing the model to various stages of the diffusion process, allowing it to learn from multi-step denoising information. We also define an efficient way to approximate log likelihoods and compute the per-token reward based on the likelihoods of current and previous policies. The final objective for UniGRPO combines surrogate rewards and a regularization term to balance the model's performance. This design captures the essential dynamics of diffusion models, enabling the model to predict answers under different masking conditions while preserving the input structure. This approach avoids the inefficiencies of previous methods and ensures robust predictions. The training process for UniGRPO is detailed in our algorithm. Section Summary. In this section, we explore how chain-of-thought (COT) mechanisms can enhance our multimodal diffusion framework by curating a dataset of long COT trajectories for tasks like textual reasoning and text-to-image generation, which promotes cross-modal synergies. We also introduce UniGRPO, a novel reinforcement learning algorithm tailored for diffusion models, addressing challenges in adapting traditional methods to improve reasoning and generation across diverse tasks. Section: Diversified Reward Modeling. In this section, we simplify the optimization goal of UniGRPO. We define the reward from the model's response and include a penalty term based on KL divergence. Our approach uses a unified reward system that can adapt to various tasks by offering different rewards tailored to each task's needs. We categorize our rewards into three types. 1. Textual reasoning rewards. We apply Uni-GRPO to the GSM-8K dataset, creating a composite reward that includes a correctness reward for accurate answers and a format reward if the response follows our specified format. 2. Multimodal reasoning rewards. For tasks like GOQA and CLEVR, we use the same correctness and format rewards. Additionally, for caption-based tasks, we introduce a clip reward that measures the alignment between text and images, adjusted to balance its impact. 3. Text-to-image generation rewards. In image generation tasks, we also use the clip reward for text-image alignment, along with an image reward based on human preferences. Both rewards are scaled to ensure they contribute equally during optimization. For text generation, we implement a semi-autoregressive denoising strategy from MMaDA, which combines autoregressive decoding with diffusion-based denoising. We divide the output into blocks and generate them from left to right, selecting tokens for denoising based on confidence scores. We set the total sequence length to 75 and perform 76 denoising steps, unmasking the two least confident tokens in each block. This method tends to produce more detailed descriptions compared to non-autoregressive approaches, which often yield shorter responses. For image generation, we use a low-confidence remasking strategy and a cosine noise schedule, treating the entire output as a single block. We generate sequences of length 1024 for high-resolution images, applying classifier-free guidance with a scale of 3.5 over 50 time steps. To train MMaDA, we utilize a variety of datasets for different training stages. 1. For foundational language and multimodal data, we use the refined web dataset and popular image text datasets. 2. For instruction tuning, we incorporate Alpaca for text and LLAVA 1.5 for visual instructions. 3. For reasoning, we compile diverse datasets for mathematical and logical reasoning, using models to generate responses and retain correct answers. 4. For reinforcement learning, we use the original datasets from our reasoning tasks. Section Summary. In this section, we simplify the optimization objective of Uni-GRPO by defining a unified reward system that incorporates diverse rewards tailored for various tasks, including textual reasoning, multimodal reasoning, and text-to-image generation. We also describe our semi-autoregressive and parallel non-autoregressive sampling strategies for text and image generation, respectively, and outline the diverse datasets used for training our model across different stages. Section: Evaluation and Baselines. In this section, we evaluate our MMaDA model on three different tasks using specific metrics and baselines. First, for multimodal understanding, we assess our model on benchmarks like POPE, ME, Flickr 30K, VQA-V2, GQA, and MMMU. We compare our results against models focused solely on understanding, as well as unified models. Second, in image generation, we measure the quality of our generated images using 50,000 prompts from our test set. We calculate the clip score and image reward to evaluate how well our text aligns with the images and how humans prefer them. We also use GenEval for general evaluation and WISE for assessing world knowledge-based generation, comparing against models specialized in generation and unified baselines. Third, for text generation, we evaluate our model's ability to follow instructions and reason on benchmarks like MMLU and GSM-8K, comparing it with models like Llama 2-7b, Qwen 2-7b, and LLADA-8b. Regarding implementation, we initialize MMaDA with pre-trained weights from LLADA-8b instruct and an image tokenizer from show-o. We conduct joint training in three stages. 1. In the first stage, we train the model for 200,000 steps using foundational language and multimodal data, followed by another 400,000 steps with more diverse image-text pairs. 2. The second stage involves 50,000 steps of training with instruction tuning data and reasoning data. 3. The final stage consists of 50,000 steps of Uni-GRPO training using reinforcement learning data. We perform training on 64 A100 GPS with a global batch size of 1,280, using the AtomW optimizer with a starting learning rate of 500 thousandths and a cosine learning rate scheduler. For multimodal understanding, our results show that MMaDA performs comparably or better than dedicated understanding models across most benchmarks, even though it was trained with a unified objective. We consistently outperform other unified models, particularly benefiting from our mixed long-COT fine-tuning and Uni-GRPO reinforcement learning stages. This is the first time a diffusion-based model has shown strong understanding capabilities, demonstrating the potential of our unified architecture. In text-to-image generation, our model achieves the highest scores in both clip score and image reward, thanks to the Uni-GRPO training stage. We also show better compositionality and object counting on GenEval, aided by our reasoning-intensive training. On the WISE cultural benchmark, we significantly outperform previous methods due to our joint training on text-based reasoning. For textual reasoning, we detail MMaDA's performance across various benchmarks, including general tasks and mathematical challenges. Despite being trained on limited task-specific tokens and open-source text data, MMaDA matches or exceeds the performance of strong baselines on general tasks and outperforms LLaDA 8B on math benchmarks. Our approach of joint training a unified diffusion model for text generation, multimodal reasoning, and image generation is a novel configuration. These results highlight the potential of diffusion-based models as versatile language models and suggest that future improvements could lead to even better performance.